Okay, so we want to do tensor products, and we want to then define what are called symmetric tensor product and Fox spaces. So that we will do on the one hand, and we will do some Hilbert space theory on the other hand. I mean, as usual. Okay, so now we have got enough theory to define what is called tensor product and symmetric tensor product. So to do that, before that, I want to define what is called a Kolmogorov dilation or a Gelfand pair of some positive definite function. So let me explain what we are doing. Before that, we have defined in the last class in the graduate analysis course, we have defined unitaries. Okay. So a unitary, if we have two Hilbert spaces, H and K, okay. It's not clicking there. I don't understand this. Something is happening. Let's start a new one. Nothing is working. Maybe there's no battery in the pencil. I'm sorry about it. Okay. Yeah, so maybe I will just use the board. I will just record it. Stop sharing or something. Yes, for the time. I don't know whether it is visible there. Anyway, so everyone knows what is unitary. So we have defined. So if you have two Hilbert spaces, HK and Hilbert spaces. Then a unitary is a map. It's a linear map. So unitary is using U in V of HK. Once again, I think the background is blurred here. So because of that, yeah. So it's a linear map which is on to is unitary. We defined this last class unitary. If it satisfies the two conditions, UX, UY, if it preserves the inner product and it's on to. Okay. So okay. So there is a lemma which when we can define, so that there is something called your, we haven't defined that. So your set is contained in H. It's said to be total. A total set is, if you take the span of that, that is del set. Okay. So you span, take the linear combination of all the elements in S. Okay. Then take the closure. That is X. Okay. This is what is called as a total set. Okay. So if we define a linear operator and a total set, then we can extend it linearly to a dense subset. Okay. That is possible. But then it's not clear whether we can extend it to the whole of Hilbert space. Further, it has to be bounded on the dense subspace. So, but then for unitaries, if it is bounded on S, you cannot say that you can, but it's bounded on the whole of Hilbert space. I mean, there is no information about it. You have to extend it linearly to a span of this S, linear combinations of all elements here, and you have to say it is bounded on that dense subspace. It is not a Hilbert space; it's dense subspace. Then you can extend. Any bounded operator can be extended from a dense subspace to the closure or completion. But if you have a unitary, then it is possible to extend it from the total set to the bigger set. So that is this following lemma item. Let S is contained in H, okay, and H and K are Hilbert spaces as before. Okay, we assume okay, U from H to K, say U naught from H to K, okay, U naught from H to K, sorry, S to K, and it is just defined on S. U naught be such that it's just a function. Okay, I am not even saying linear. I'm not, there is no condition. It is just a function. Okay, just some function from S is just a set. Okay, there is no linearity or anything. Okay, it is just a set. Okay, so you have a set and it's just a function satisfying with inner product. It results in inner product. U naught X, U naught Y equal to X. Okay. Then there exists a unitary operator. There exists isometry. U from H to K, maybe not to H to K, such that U restricted to the S is not. So if we have an inner product preserving function defined on S, okay, then you can extend it to an isometry. You don't, once it is given, it's preserves inner product on a total subspace. You don't need to verify it is well defined on the linear. See, if you are extending something from some set to linear combination, then you have to verify that it is well defined. For different linear combination, you can have the same element, you can arrive it at through different linear combinations. You have to verify that all these things are not needed. Okay, there exists a well defined isometry. Maybe all this well defined, everything will be satisfied. So it's a very nice lemma, of course. It's unique, yes. There exists a unique isometry. I mean, if some linear operator is defined on a total set, it coincides on total set, then it is. Well, I mean, it may be extended, it may not be extended, but if there is only one operator. If it is extended, I mean, if it coincides on a total set, it should coincide linearly. So it should coincide on the linear span of it. And since they are continuous, they have to be, they coincide on that closure.
So you not have to be linear on S.
On linear, no. I'm saying it's defined on S, linear on S. But when you are extending it, it's linear.
Yeah, I mean
later it is linear.
U naught itself is.
Yeah, U naught is not linear, but the extension is unique because that extension is a linear operator. So extension will agree on S. So if a two linear operators agree on S, then they have to be same. Okay, so the extension is same. I'm not saying nothing about U naught. That U naught, you cannot talk about linearity because S is not a subspace.
No, what if S is the subspace?
S is the subspace. Then it has to be linear because it satisfies this condition.
Okay.
Anything we satisfy. See, the point is anything we satisfy this condition, any function will be unitary.
Yeah.
It will be automatically linear.
Yeah.
Okay. Okay. Proof. After this proof, maybe I will try to write it in the iPad.
Instead of like a total subspace is the entire space.
Total subspace, yeah. Yeah, total. No, it can be dense. Yeah, if it is subspace, it will be dense. Yeah. If it is subspace, it will be dense, right? Okay. So proof is very easy. So suppose I mean, if we extend U naught linearly to span of yes, first span of yes, and we have to show that it preserves the inner product on that. So then it's a unitary on yes. Okay. Then if it is a unitary on S, then we can extend it to the bigger one. So if it is unitary, if it preserves inner product, then it will preserve the norm. Okay. So then it will be a 1-1. It will automatically well defined and automatically 1-1. All this is please verify this. Okay. I mean, convince yourself. You just write the definition, it will come. Okay. So we can extend it linearly. So suppose now what we want to do? So let X is equal to, I mean, so So let x is equal to summation lambda I si and y is equal to summation mu j pj. Okay. Then, so we extend u naught linearly to u on span of it. Then u of summation ux uy equal to summation lambda I si u naught. So it's linearly you are extending, so it has to be like this. Okay, summation mu j u naught ej. You take it out, summation lambda I bar. So here our inner product is conjugate linear in the first variable. We are doing quantum probability, so it's conjugate linear in the first variable and linear in the second variable. Okay, so meaning times summation u naught si u naught ej. So here it's, so this is just lambda I bar mu j. We just take it inside and we will just inner product. You just take it inside and inside. So linearly inner product it comes out and goes inside, but for a norm this will not happen. Okay, so if a linear operator, for example, if you for you, I mean you should remember this fact that if a unitary, if it preserves norm on a subspace, norm on a whole space or subspace, then it's unitary. Then it will preserve the inner product also because of polarization identity. Okay, but if it preserves norm on a total set, it will not preserve the inner product. Okay, because the polarization identity requires some linearity among them, so it will not. So it need not be even bounded. It may be preserving norm, or it may be bounded. So you may not be even able to extend it in a bounded way to the biggest whole space. Okay. So only when it preserves the inner product, then you can extend it to a isometry. Okay, and I forgot to write something, so I will write it here before that. Okay, U is unitary if U naught S contained in U naught S, the range of this U naught S contained in A is total. That is clear, no? So U naught S is total. So the range of U will be, so if U naught S contained in A is total, then so I have to say something. Then U of H is dense, like, because it's total. This is just the linear combination of H is just the linear combination of this. So you can take UH is total. UH is dense there. Okay. Now, but UH is closed. But U is an isometry. But then the range of isometry is closed. I will prove it. Okay. Range of isometry is closed. Okay. So UH equal to K. Okay. I hope you can see. I'm not, it's maybe not a video. So you just look at it if you have any doubt. So next one I will write. So you have to remember that. So you have to remember that this is only true for unitaries. I mean for functions preserving inner product. And if it is on, I mean if the range of S is total under U naught, then you can, then it's a unitary. Okay. Okay, now I will become. Okay, so we have proved the following lemma. Okay, lemma. Just write it here. So H, K, Hilbert spaces. We'll quickly write it. H K Hilbert spaces. S contained in H is total. Okay. U naught from S to K such that U naught XY, U naught X, U naught Y equal to XY for all XY in S. Okay. Then there exists an isometry, then exists a unique isometry U from H to K such that U restricted to S is equal to U naught. Further, U is unitary if and only if, it's clear only if U naught S is total in K. Okay. So this is done. Okay. Okay, so the next one we want to prove. So we want to construct what is called a Kolmogorov dilation or a Gelfand pair. I don't know which one is. Both names are there in the literature. So, incidentally, all these things are in the first section or chapter. It's the second chapter of KRP book, KR Parsarthi book, Quantum Stochastic Calculus. All these things, what I am doing, it's in the second chapter, first section. Okay, the very first section. Okay. So the definition. SD any set. This is how to construct a Hilbert space out of any set. Any set. Okay. You have some set, but you need something else to define another product, to get a Hilbert space. How do you get a vector space out of any set? You just consider functions on that. Okay, that's one way. Then you need to define an inner product. For that, you need something else. So that is why this positive definite function. So that is this K from S cross S to C is a positive definite function. This is the definition of positive definite function. Okay. Positive definite function. A function is positive definite if for all x1 up to, if you take a finite subset of S, x1, x2 up to xn, you take a finite subset of S, okay, then the matrix, you can define a matrix. So you better, I will write the actual definition also. Then the matrix, you can define a matrix K xi xj. Okay? I mean, kxy is a function, so it's a complex number. So this is a matrix contained in M and C. Is positive definite. Is positive. Okay. What does this mean? That is for lambda 1 up to lambda n contained in Cn, okay, lambda equal to this. This matrix you call it as Kn or something. Kn lambda, this inner product is greater than 0 for all. Okay. Right? This is what positivity means. The definition of positivity is this. Okay. I'm just saying, if you have a set S, you have a function, two variable function defined on S cross S. That function is called positive definite. You can consider the matrix K xi xj. Okay, I mean this is a matrix entry. Ijth entry of Kn is xi xj. Okay? Or maybe not. Okay, you call it as, I'm sorry. You have x bar equal to this, then call it as kx bar. Okay? This is a matrix. So this matrix is positive. Okay? By positivity, we mean precisely this. Okay, inner product of lambda with kx lambda is greater than or equal to 0. That is, what does it mean? So what is this inner product? So this inner product is, this is lambda I. This is a vector lambda I equal to 1 to n. But then kx multiplied with lambda is summation k xi xj, right? Then lambda j, right? And this is also I equal to 1 to n. Here the summation over this j, right? This is what the matrix acting on a vector is. So this is equal to summation lambda I bar, lambda j, k xi xj. This number is greater than or equal to c. This is what the meaning of the function being positive definite. Okay. So let me show the full definition. S is any set, then K is positive definite if it satisfies this condition. Summation lambda for any, this is for any x1 up, this is true for all x1 up to xn contained in S. I mean, this is true for all x1 up to xn contained in N and lambda 1 up to lambda n contained in C. So you take any n complex numbers and n elements of S. S is some set. So then this is satisfied. This is what is called positive determinant. Okay. Now this is the theorem. This theorem is either called as Kolmogorov dilation. We will call it Gelfand pair. Okay. It's also called Kolmogorov dilation or a Gelfand theorem or Gelfand theorem. Gelfand theorem. Okay. So the theorem is the following: S be any set and K from S cross S to C is positive definite. Okay. Okay. Then there exists a Hilbert space. So it depends on K. So maybe we call it as HK. Okay. And a function and a V from S into HK such that V of X, V of, V of X is inside, correct, I originally correctly. Okay. Vx, Vy equal to Kxy. Okay. Yes, and V of S is total in HK. So if you have a positive definite function defined on S cross S, then you have a Hilbert space where you can embed this set S into that as a total subset. Okay. And this inner product will be exactly given by the Kxy. So that is the theorem. Okay. That's all. The Kxy is the whatever the positive definite function you have, that's a inner product. Okay. Kxy will be an inner product. To see any positive, any inner product is a positive definite function to start with. If you have an inner product on a Hilbert space, H is an Hilbert space. Okay, inner product is from H cross H. I will erase it. H cross H to C. So if you have any summation lambda I bar lambda j, some xi, xj. Right? This is Ka, Kj, no. So which is this. So this is equal to summation. This is you can write it as summation lambda I xi. Again, summation lambda I xi. That's what you have, which is greater than or equal to C. Okay. So any inner product is a positive definite function on any Hilbert space. Okay. But here what we have is, we have some set where you have a positive definite function. Then you can embed, you can construct a Hilbert space and you can embed this set. Of course, you can't expect that set to be a Hilbert space or a vector space. You can embed this set into a Hilbert space as a total subset. And the inner product will be given by that positive definite function.
The dimension, can we say anything about it?
You cannot say anything about the HK. It need not be even separable. Under some conditions, when we know the Hilbert space explicitly, then we can say it's separable or something. We have to prove it separately. Nothing is guaranteed from the property of S.
We just know
There is some Hilbert space. It need not be even separable. Okay? But in our cases, whatever we need, it will be clear that it will be separable. Okay?
For finite case, it will be just
yeah, but finite case, yeah, it will be finite dimensional. No? It will not be cardinality differential. It will be functions on that. It depends on K also. Okay. So if you have just K, if you have K xy equal to delta xy, for example, then it will be just Cn. whatever, C of S. Okay. Otherwise, it depends on the K. I mean, it depends on the K. Okay. So proof, this is an abstract construction. Okay. So once we have this theorem, we can construct Hilbert space out of positive definite function and other things, okay, which we use it frequently. Okay. So what do we do? So there is nothing else. We have just a set. So we want to get a Hilbert space mean, we have to consider functions and then define an inner product on that. Okay. But then we will consider functions with finite support. Okay. So let L equal to all functions from S to C such that f of S equal to 0 except for finitely many yes. Okay. So f of S is f has finite support only for finitely many of yes. We take such functions, such collection of functions. Okay, the dimension will be, this is not a finite dimensional. I mean, finite support. It's only has finite support, but the number of functions will be. I mean, this vector space L will have dimension which is it will be infinite dimension. It's not a finite dimension. Okay. Now define inner product on that. Define. So this is I call it inner product of Fg naught. Okay, because this is not the inner product we want. That is equal to summation yeah, f of S bar G of S G and F I think it should be summation f of S bar G of T ST in S and K ST. K is capital K. But then this will only be finitely many of S and T, this will survive. Okay, so this is just a finite sum. Okay. I mean, it is like the F has a support, some S1 up to Sn. T has a support, T1 up to Tn. Then you can take the union of those S1 up to Sn and T1 up to Tn. So it is only on this F and G, both of them are non-zero. Okay, if at all. I mean, outside this set S union T, it's 0. Okay. The sum is over S union T. Okay. And it is like the by earlier positive definite definition. Yes? Intersection. You are taking the product also. Yes, intersection. Correct. Yeah, that's what will happen. So it's a small set. And you have to take the K also only in that set. And the positive definite. So verify. I mean, it's clearly conjugate linear in the first variable, linear in the second variable. Those things are clear. Okay. And you have to verify this is a semi-inner product. Okay. Verify this is a semi. There is nothing to verify. Positivity you have to verify. When if you have FF, then it is positive because of positive definiteness of the convince yourself. Okay. There is nothing to verify. If you take FF, it's clearly conjugate linear in F, linear in G. And if you have inner product, it's not inner product. If you take the FF, okay, FF bracket, then that's going to be greater than 0 because of the positive definiteness of that. Okay, is semi-inner product. On L. Okay. Okay. So now I define N is equal to all those F in L such that this FF is equal to 0. Okay. And let H naught is equal to L quotiented with N. Okay. And define inner product of F plus N, G plus N equal to F G naught. Okay. This is an inner product on H naught. This is an inner product. This is the claim. I have to prove it. reason. So it's clearly conjugate linear, the first variable, linear, the second variable. That's okay. You have to only verify the positivity of the inner product. Okay. So suppose what I have to verify? I have to verify the positivity of the inner product. Suppose f equals 0. Okay. That means, so when, I mean, here f and g are, ff is not equal to 0, gg is not equal to 0. That's what it means, right? N is N is the kernel of the inner product. Okay, ff equal to 0. The inner product of f with f is 0. That's what the inner semi inner product of f and f with is 0. All those elements which are 0 is n. Okay. So now if suppose the inner product is 0, ff is 0 means, so I mean, first of all, we have to verify it's well defined. So positivity is clear. The well definedness is what we have to verify. Okay. So is a well defined inner product. Sorry. Is a well defined. Well defined means it does not depend on the element in n, right? See, the f plus n means you can add some element in n. That's what it means. Okay, so well definedness. So for verify well definedness, you have to verify f plus n1, f plus n2. Okay, I mean, this inner product is exact, of course, equal to f, I mean, g plus equal to fg naught, right? Why is it true? Because if you take fn2 is less than or equal to mod of this is less than or equal to norm f, this inner, I mean, this norm f thumb norm n2 equal to 0. Similarly, if you take n1g, this is less than or equal to norm n1. This is Cauchy-Schwarz, okay, which we have proved. n1 times norm g, which is equal to 0. Okay, so those inner product are 0. Okay, I mean, since n2 is in n, script n, that is in the kernel, inner product of any f with n2 is also 0 because of Cauchy-Schwarz, okay, because of the inequality. And of course, we know n1, n2 is also 0 because by Cauchy-Schwarz. And so this is also less than or equal to, so I have to put a naught here, okay, n1 naught, n2 naught equal to 0. So because of all these things, f1, f plus n1, g plus n2, that inner product, the not inner product is exactly equal to fg.
How do you know that inner product of f comma g naught is like a bounded operator?
Inner product of f.
When we take the null space and quotient it, we need the null space to be closed. For that, we need like a bounded.
Null space is closed because inner product is, it's a genuine inner product. Inner product is continuous. Semi inner product is also continuous because of Cauchy. I mean, we proved Cauchy-Schwarz for semi inner product. Okay.
Yeah, how do we know it's continuous? That's my
inner product is semi inner product is continuous because of Cauchy-Schwarz inequality. Okay.
okay.
N is closed. Let me write here. This is closed. Your good question. It's closed since this is continuous. It follows from Cauchy-Schwarz. We proved Cauchy-Schwarz for any semi-inner product. And any semi-inner product, we see, if you have linearity and conjugate linearity, then Cauchy-Schwarz is there, and because of Cauchy-Schwarz, it's continuous. Okay. Cauchy-Schwarz is very powerful. Okay. Because of that. Good question. Okay. And also this conjugate linearity, then fg inner product bar is gf. That's also satisfied here. Okay. That's important. It's not just some linear form, it's inner product. Okay. So we have quotiented it with something. Okay. So this clock is not working. We got h naught. Okay. Now let h is equal to, I mean, and positivity is clear, of course, right? First, I mean, if f plus n, f plus n, this is equal to f naught equal to 0, implies F is in N. Okay. So that's what the zero element is N in the quotient space. The zero element is N. Okay. So this implies this is positivity. This implies, I mean, F is in N. That is, F is equal to 0 in H naught. Okay. Now let H is equal to the completion. And we have it verified, but I mean, if you have any metric space, then you can complete it. The same is true for Hilbert space. You can complete it, but the inner product will extend to it. Okay? In fact, any linear map will be extended. So you have to verify this. I didn't give it as an exercise or something. Okay. I didn't do it. Usually it's an exercise, but please convince yourself. And inner product can be extended and to the completion. Okay. This is just the metric space completion, but it's still in an inner product space also. Okay. So this is our Hilbert space. So we have constructed a Hilbert space. Okay. Now V of S define V from S to H. V of X, V of any X is equal to this delta X. Okay. What is delta? Delta X is just delta X of Y equal to 0 if X not equal to Y, and equal to 1 if X equal to Y. Okay. This is the delta function. That's how we defined V. Then you consider the inner product delta X delta Y, which is equal to summation, I mean, K X prime Y prime delta Y of.
Sorry, I didn't get it. What is delta X?
Delta X is the delta function. Delta X at X is 1. Delta X at Y is 0 if X is not equal to Y. It's the delta function. And if we take the inner product, delta X, delta Y, the not inner product, that is going to be KXY, delta Y of X and delta X prime and delta Y prime, sorry, Y prime and delta X of X prime, which is equal to just KXY, right? Okay. This is just KXY. Fine. Maybe there's a bar, doesn't matter because it's going to be 1. Okay. Okay. So we have proved that Vx, so this implies inner product of Vx, Vy is equal to Kxy. Okay. And delta functions are total. Any function with finitely many of them. Okay. You are taking actually any finite function with a finite support can be written as sum of delta functions, right? You take the support and you just write it the summation lambda I. So any function with finite support can be written as linear combination of delta functions. And that's enough. I mean, that's a dense set. Okay. I mean, we are taking the function. I mean, this H is not all functions with finite support. Functions with finite support are dense there. We are taking functions with finite support and we are defining an inner product. Then we are quotienting the null space. Then we get a function space, new function space, which is a quotient space. Then we are completing that. Okay. So functions with finite support is dense there. I mean, in a sense, up to the quotient, it is dense there. But functions with finite support, you can get it from delta functions. Okay. I mean, maybe I should say delta X plus N, maybe, because delta X may be in N. Okay. I mean, just to make it precise, delta X may be a function with 0. I mean, because K is because of K. Okay. Then it will be a problem, no? No. K.
Like in the quotient, let me go to 0. So
No. We want V to be no, it will not be 0 because see, it preserves the inner product. No, K is a positive definite function. Okay, Kxy is strictly greater than 0. Kxx is no, there is no condition like that. It is only greater than 0. Okay, there is no condition. There is nothing like 1, 1 or something. It's okay. It is just the image of V is total. That's all. Okay, this is okay.
Delta X, with set of all functions of the form delta X forms a basis of L, right?
Basis of L. I mean, not basis. It's a total. I mean, basis means it should generate the whole thing. It will be dense. The span will be only dense there.
So it will be generated because L we assume is set of all functions with finite.
Oh, L it generates, right? Not H. H is the closure.
Oh, H is the
That will have
closure.
infinite support. Okay, so. Okay. Okay, H is bigger space, much bigger space. Okay, now there is some uniqueness. Okay, there is uniqueness. So maybe I will write it here further. Part of proposition. Further. I will write it here itself. Further. Part of theorem. I mean, the Hilbert space is unique, but then Hilbert space is unique means it's unique up to unitary. Okay. Further, I mean, we say something is of course. So maybe I'll write it as a definition and then we'll say. So the definition. This pair, this H with V, H with a K, no, whatever, H with V is a Gelfand pair. Gelfand pair for S with K. Okay. If there exists a V, if there exists V from, I mean, if you have a V from S to H, such that V of S is total in H, and Vx, Vy equal to Kxy. I mean, we have constructed one, but any such thing satisfying this is called a Gelfand pair. Okay. Now the proposition is the Gelfand pair is unique. Okay. For that, we will use the what is in the board, the unitary, the lemma. This lemma we will use. Proof. So suppose H1, H2. So H1, V1. H1, V1. And H2, V2. V2 Gelfand pairs. I mean, what do I mean by uniqueness? There exists a unitary from H1 to H2, which intertwines this V1 and V2. Okay, maybe I will write it here. I don't know if I'll be able to give the gap. Which is okay. Okay, that is. That is, there exists a unitary from H1 to H2 such that U star will take it from H1 to here, V1 is equal to V2. Okay. That is what it means by its uniqueness. Okay. I mean, we say some Hilbert space is unique or something when there is a unitary between them. We say some operator is unique if this U star is bringing it back, the inverse. And then here this operator will act, whatever the operator or function. Then you push it back by U. That should give the other one. That is what is uniqueness in terms of operator or functions or whatever.
Okay? So V is a function on S, right?
P is a function on S, right? Yeah.
U star is from H2 to H1.
Yeah. V2, wait a minute. V2 is a function acting on that. What is it saying? So, okay, let's just write. So you have
U of V1 of S is V2 of S.
V1 is a function from S to H1. and is also a function to H2. Okay. Sorry. V1 should be there. V1 inverse. How do we write V1 inverse? V1 may not be invertible, no?
Maybe this thing.
Unless Kx is strictly positive, V1 will not be invertible. Let me rest with the inverse. I'll write and then we'll get the right one. So it's like V1 inverse, then V2. What? It's not here. Unitary is here. Okay. Yeah, unitary is here. Then V1 is here.
There
V2.
should be unitary composed with V1 is equal to V2.
That's all, right? That's all. Yeah. So this is not an operator. Okay. This is just V2 is equal to V1 composed with unitary. Okay. That's how it works. Yeah. Yeah. Good. So, yeah. V1 lands in H1 and you apply it and you get this. Yeah. Okay. Okay. Now we have two Gelfand pairs. Okay. So as I said, you need not even verify the what is called well-definedness of when you define like that. Whatever this like this. Define U naught from V1s to V2s by V1x going to V2x. Okay. Then V1x V1y equal to xy, sorry, kxy. Equal to V2x, V2y. Now extend by the lemma. Lemma 1, or the first lemma of this. If you have some function from a total set to some Hilbert space, from a Hilbert, some set contained in a Hilbert space, total set to a Hilbert space, then you can extend, which preserves the inner product, then you can extend it. If it preserves the inner product, then it has to be well defined. It will preserve the norm, so it will be well defined. And if you have two of them, okay. So we have proved the. So there is no. Oh, I've taken 1 hour to prove this. Okay, now let us define the tensor product. Okay, so let tensor product. So H1, I directly define n tensor product. You can define it for 2. You can define it for n. Doesn't matter. H1, H2, Hn. B Hilbert spaces. N Hilbert spaces. Huh? For finite dimension.
Yeah.
Finite dimension, but it's the same thing. Same thing, but I'm using, precise notation. I just said you take formally extensor y or something. Okay, then you have to quotient it with some algebraic operation. But here everything will be contained in the construction. What you are quotienting it. See, it is like you have linear combination of the first one or the second one, doesn't matter. See that those things you have to quotient it, and it will all be contained in the construction. Okay, so this is the proper definition. Okay, H1 up to see, it's the same thing. You take formal thing, except I said it's a linear combination of elementary tensor. Here you have to take the linear combination and close it. That's all. Here it is just the completion. That's all. Okay, we Hilbert spaces, then define K from take H1 cross Hn cross H1 cross Hn. It's a positive definite. It's a positive definite function defined on H1 cross H2 cross Hn. Okay. I'm just writing it again. H1 cross H2 cross up to H cross Hn cross, again the same thing, H1 cross H2 cross up to Hn. Okay. Where if you have some U1 up to Un, V1 up to Vn, that is equal to the product of inner product Ui, Vi. I equal to 1 to n. Just the product of them. Okay. So it lands in C, correct. Okay. And this is a positive definite. So this is K. Okay. K of this is equal to this. Is positive definite. I mean, it's clearly positive definite. If you have some n number of them, if you have a scalar, then the scalar you can take it inside one of them if you wish. Okay. And then it is just the property of the inner product. Okay. Inner product is positive. Okay. So verify. It's positive definite. So the Hilbert space that we get out of this is what is called the tensor product. Okay. H1 tensor Hn is the Gelfand pair. Is the Gelfand pair. Gelfand pair associated with H1 cross up to Hn and K. Okay. That's okay. So notice I mean, what is see? So you can denote. You have a V, okay, which is x1 cross up to xn. You denote that as x1 tensor up to xn. Okay. You can just denote it like that. Gelfand pair means you have a V, which is defined on the H1 cross up to Hn, and it takes it inside. See, this is the direct product, H1 cross up to Hn. That is not, tensor product will not look like that. Tensor product is much bigger. Okay. Those kind of elements are total elements there. Okay. So now we have a V from this direct product inside the tensor product. Okay. You denote those elements as x1 up to xn. Okay. Then, of course, by whatever we have done, x1 up to xn with xi in hi is total. I mean, you have to take the span of that and then they take the closure of that. That will be H1 tensor Hn. I forgot to give something. So just to understand this, I give this assignment. Okay. S be any set. Okay. And define K xy equal to 1 if x equal to y and equal to 0. It's delta function. X equal to 0 and equal to x not equal to y. Okay. Then the Gelfand pair is just L2 of S. I mean, what is L2 of S? It is just you take, but it's an uncountable thing. You take countably thing, but it has to be summable in our sense, the net and all that, whatever you have said. Okay? Absolutely summable in that. It is just L2. It is not that there is no, I mean, if for it to be summable in a different sense, you need measure or something. There is no measure. It is that finite net should converge. When it converges, it will be actually, it will have the support only countably in many places. It cannot have uncountable support. Okay? That you can get convinced. Okay? So it is just L2S. So that you prove it. Okay. It's same as this. You take finite nets and then it's a limit of that. Okay? This one. So then it is clear if S is finite, then under this kernel, this is K is called kernel. Under this kernel, it is just Cn. If it is a finite set, and if you have the kernel as this delta function, and you know that V of any x is equal to delta x. Okay. The function delta x, the function delta x function. Okay. What is what is delta x? L2s means L2 is a function, no? So it is 1 in the x place everywhere is. Okay. So this is an assignment, very easy assignment. Just verify that. Okay, now we are discussing tensor product. So we want to have some more properties. First, we noted that. Okay, what is the second one? And maybe I'll write it as a proposition. Okay. X1 is dense there, and the function x1 cross up to xn. See here, I mean, usually we have a set, and then we define a kernel on that, positive definite function on that, and get a Gelfand pair. But here that set is yes, Hilbert space, direct product of Hilbert space, set direct product, h1 cross up to hn. Okay, so you can talk about multilinearity. Okay, this function going to this x1 tensor up to xn is multilinear. That is, if you have a lambda here, somewhere in the lambda xi, you can take it out. See, these things are sitting in a vector space, right? So you have to, there is some subtlety here. Each xi is coming from a Hilbert space. Okay, so you can multiply each xi in the elementary tensor by a scalar, or you can add two things among, I mean, you can inside the tensor. Okay, but then there is a summation in the Hilbert space you have constructed. There is a scalar multiplication there. So it's same as that. Is multilinear. Let me write the definition. What it means. It's multilinear. That is, you take any of them. X1 cross up to alpha xi, alpha x1i plus xj. Okay. Then cross up to xn. Where anywhere. This alpha beta can come anywhere. Okay. So this V of this equal to alpha of x1 tensor up to xn, where here x alpha of x1 tensor up to here you have x I here, I mean, I'm putting the 1 in the first place, 2 in the second thing. Okay, x1i tensor up to xn plus x1 tensor x2i tensor xn. This is clear, no? This is happening, this alpha beta, whatever is happening in the tensor Hilbert space. There the alpha is in the individual Hilbert space hi. Okay, so this map is multilinear. To prove that this map is multilinear, you have to take the difference between that V of whatever. I mean, what is V of this? This is same as this. I mean, you don't have to erase, you can write it if you want. Okay, what this V of V is just nothing but this x1 tensor up to alpha x1i plus beta x2. There is no beta. 1 is enough. x2y tensor xn. Okay, these two are equal. That's what I mean. Okay? You can take the alpha out and the summation out. It is some sort of distributivity between the sum and this. Okay, you can take it out. That's what it means. Okay, so this is what multilinearity for all xi's and alphas in scalars and those things. Okay, proof. To prove that these two are same, what you have to do is take the difference and the norm is 0. Right, that's what it means. These two are equal in the Gelfand, whatever the Gelfand pair you have defined. Okay, and so that is what. So first thing you notice is in the Gelfand pair, whatever we have, x1 tensor up to xn and y1 tensor up to yn is equal to inner product xi yi. Okay, that's what we have defined. Then inner product between the, see, this is what I said earlier. To define the inner product, you take formally elementary tensor and you define the inner product on them. Then you take the linear combination and close it. You just write it formally, which is okay. Here we have rigorously defined it. That's all. That's the difference. Okay. So this is clear because that is how it is defined. Okay, because that is how the K is defined, which is the K of this times this, which is equal to this. Okay. Okay. Now we want to consider this. This is little bit messy. Is there messy? I don't think so. Okay. Now Let us calculate this. What do I have to do? I have to verify this. Norm of the first one. I'm going up, sorry. X1, maybe I'll put here. X1 tensor up to alpha x1I plus x2I tensor up to xn. Okay. Minus x1. So alpha times x1 tensor up to x1I tensor to xn. Minus x1 tensor to x2y tensor to xn, right? This norm. But then I want to use inner product, so I put a square. Okay. Okay. Now this is equal to what will happen is, of course, we have three of them. We have two of them, you know how to compute the norm square. Norm of first one square, norm of second one square, minus two times real part of the inner product between them. But when you have three of them, it's like a plus b plus c whole square formula kind of thing. So you will have the square of first one, square of second one, square, and the real part of each two of them. Okay. So this is equal to. So, but then if you take the norm of these things, everything has the other things are common, right? Summation of I j not equal to I. Okay. J not equal to I. Norm xi square. This will come out from all of these things. Let me write it and it will be clear. Times norm of alpha xi1. The first one, alpha xi square plus x2y square, right? Plus mod alpha square plus x1i norm of square plus norm of x2y square minus 2 real part of alpha x1i plus x2y times alpha of x1i minus 2 real part of, I mean, it's clear now. I just have to write all these messy things. And so it is, next one is alpha x1i plus x2y into x2y minus 2 times real part of, it's minus, no? Minus, this will be plus, I think. This will be plus, minus. So this will be plus alpha x1i, x2y. I think it's okay. But then you know that this is 0. If you expand the first one, you get the rest of the thing, right? No. What do you get? There is one more thing coming here. Is this 0? I have minus here.
I think we can expand the inner product also.
You can expand what?
The inner products.
Inner product of what?
The real parts.
That means get another alpha x. Yeah. This will give alpha xi square. That will go away. And this will give alpha xi, that will go away. Correct. And the first one, when you expand it, you get the other two things cancel. Is okay. And if I verify, this should be equal to 0. There is no other way. Sorry, not equal to 0. It's equal to 0. Okay. Convince. Verify. Okay. That's all. So this says it's linear, multilinear. Okay. So we have proved, and we have, what we have elementary tensor is, you have elementary tensors and you know the inner product between them. That is how we define the inner product, tensor product initially, and that is a total subset. Okay. Now we define a new kind of tensor product that is called this. So if you take just two of them, or you can take n of them if you want. So you take HB a Hilbert space. This is the definition. HB any Hilbert space. Hilbert space. Okay. Then define H. I put a S here like this. H, S, H. This is it. Definition. Is equal to all those xi in H tensor H. H tensor H itself. Okay. Such that U sigma of xi. I will tell you what this means. Equal to xi itself. Where this is true for all sigma. Let me explain what it means. Maybe I will write it and then explain everything. Okay. For all sigma in S2. Where S2 is the permutation. Okay. S2 is permutation group. So two permutations. Okay. Okay, where U sigma of X tensor Y is just permuted. That's all. I mean, it is just the equal to, I mean, X sigma inverse of 1 sigma Y, X1 tensor Y1. That's what I should write. Yeah. X1 tensor X2. Then it will be clear. X2 sigma inverse 1 and X sigma inverse 2. You have to put inverse so that it will be a representation. I mean, it's okay if you put sigma inverse. For this definition, it's okay. But usually it is customary to put sigma inverse because that will give a representation of the unit. I mean, this group. I mean, when sigma and some sigma 1, sigma 2 is composed, the unitary opposite should also compose the same way. Otherwise, it will be the opposite representation. Okay. So it's not relevant here in this definition, but it's better to put sigma inverse. Okay. This is what is called symmetric tensor product. Notice that this U sigma is defined only on elementary tensor. Okay. Then U sigma of X1 tensor X2, U sigma of Y1 tensor Y2 equal to X1 tensor X2, Y1 tensor Y2. That is clear, no? Because when you apply the sigma, it will permute the right places and you will have the product, and the product you can permute whichever the way you want. Okay. So that preserves the inner product. Okay. Now we extend. This is only defined on elementary tensor. Extend U sigma to H by lemma. See, the lemma is so useful. It comes everywhere. Okay. You have only defined this U sigma, this lemma in the board. U sigma is defined only on the total set. Now you can extend it by that lemma. Okay. So you have some set and it preserves the inner product on that set, total set. Elementary tensors are total in the tensor product. So you have defined U sigma by permuting the elementary tensors. Okay. You can just permute it among themselves and then you can define it on this. Okay. So now that is how U sigma is defined. U sigma is a unitary operator. Okay. Extend U sigma by lemma as a unitary operator. Okay. Now all those elements which are fixed by the unitary, all this permutation is what is called the symmetric tensor. Okay. This is what is called symmetric tensor. Okay. Okay. Now I give a slightly non-trivial assignment. Okay. And start. Assignment 2. You can submit after the midterm. Okay. Assignment 2. The earlier one also. If you have submitted, it's okay. Otherwise, submit everything together after midterm. Okay. I mean, if you have already submitted something, then it's okay. Okay. You don't have to resubmit it. Okay. Assignment. Okay. So H be any Hilbert space. Okay. Now define K of XY equal to, you take the inner product and square it. Yeah, square. This complex number square. Just square it, okay? Then Gelfand pair is isomorphic. I mean, the Gelfand pair is the symmetric tensor product. That's what I want to say. But then how the isomorphic to the symmetric tensor product, HSH, with V of any X equal to X tensor X. I mean, yeah, X tensor X is fixed by permutation, no? So that is an element in H, this. Okay. H, symmetric tensor H, this is S, okay? And X tensor X is fixed by permutation. Okay. See, there are many things which are fixed in the permutation. For example, X tensor Y plus Y tensor X. Yeah. This is fixed by permutation. Because our U sigma is defined on the elementary tensor, then we are extending linearly and then to the completion. Okay, so this is a linear combination. So if you apply U sigma, then this is fixed for any sigma, right? So there are many such elements. Okay, so I am just saying if you take the kernel to be this xy square, then the Gelfand pair is exactly the symmetric tensor. Of course, up to isomorphism, you have to prove that they satisfy all that. Okay. This is also trivial. You have to verify that. So there is nothing. Okay. So this is the Gelfand. Okay. So I think I will stop. Here everything stopped here. The screen. Oh no, I didn't notice this. In the screen, everything is stopped here. In this, I was looking there. Anyways, I'm sorry about it. Why is it stopped here? I don't know.
Maybe for this lecture, you can just upload them.
Huh?
Just upload the notes for this lecture. Don't need to
Okay, yeah.
add the video.
Yeah. Yeah. Okay. Okay. So we'll stop here.